To set this particular multifunction timer to perform the cumulative on-delay function using a period of 5 seconds, a technician would rotate the function selector to function H, the cumulative on-delay function with auxiliary, as illustrated in the table. Then a technician would choose an appropriate delay period. This particular manufacturer necessitates a two-step process to adjust the delay period. First, select the range, then adjust the range percentage. The range selection presents possibilities from 1 second up to 100 hours. The percentage can then be used to fine-tune the delay period inside this range. For example, 50% of 10 seconds would be a delay of 5 seconds, as would be 5% of 100 seconds. However, 50% of 10 seconds would allow finer tuning around the 5-second region. Note this timer has two indicator LEDs, one that indicates when the device is powered up, and another that indicates when the outputs are in their activated states. Unfortunately, it does not have another LED indicating when the auxiliary controlling input is inserted. This would be a great feature, but sometimes you got to work with the tools you've got on hand. You know you set up a cumulative on-delay timer out correctly if you power up the device, assert the controlling auxiliary input for a couple seconds, assert it again for a couple of seconds, and after an accumulation of 5 seconds of assertion, see the output change states. When the controlling input is de-energized, the associated contacts immediately return back to their deactivated states. The cumulative on-delay function seems to work just fine. Troubleshooters take note. A multifunction timer executing the right function at the wrong time needs to have the delay adjusted. In contrast, a multifunction timer executing the wrong function at the right time needs to have the function adjusted. I'd like to say that the misinterpretation of functions is a rare occurrence, but it isn't, and you need to be aware of this possibility. Let's now move on to the remaining topic of this lecture, putting the timer executing the cumulative on-delay function to use. For these examples, we'll make use of a multifunction timer that necessitates the coil be continuously powered and requires the use of an auxiliary controlling input, as illustrated in this particular timing diagram. The classic introductory example of a cumulative on-delay timer is the time-delayed response of two pilot lights. Note the coil of the timer relay is continuously powered by the connection in rung 1. Opening stop would serve to completely depower the timer. Start in rung 2 serves to energize the auxiliary controlling input of timer relay TR1. Rung 3 contains a normally closed contact, TR1A, associated with timer relay TR1, executing the cumulative on-delay function in series with a red pilot light. Rung 4 contains a normally open contact, TR1B, associated with timer relay TR1, executing the cumulative on-delay function in series with a green pilot light. Let's assume the timer executing the cumulative on-delay function is set to execute a 5-second delay. Note the start state of the circuit is red light on, green light off, the timer is powered up, and the accumulator has 0 seconds. When an operator presses start, the auxiliary input of timer relay TR1 is energized. If an operator presses and holds start for 1 second, then releases it, the accumulator has accumulated 1 second of a total 5-second available countdown. After a pause, let's say an operator presses and holds start for 2 more seconds, then releases it. The accumulator has now accumulated 2 more seconds. This additional 2 seconds is added to the 1 second already in the accumulator, meaning the accumulator has now used 3 seconds of its available 5 seconds. Finally, after another pause, let's say an operator presses and holds start for more than 2 seconds. This additional 2+ seconds is added to the 3 seconds already in the accumulator, meaning the accumulator has used all of its available 5 seconds. And the timer signals its associated contacts to immediately change states. The red light turns off and the green light turns on. As long as the operator holds start closed, the contacts will remain in this activated state. The moment the operator releases start, the associated contacts return to their deactivated states. We've returned to the start state of our system. Red light on, green light off, accumulator is back to 0. This circuit therefore only responds after an accumulation of 5 seconds has occurred. Importantly, the cumulative on-delay function differs from an ordinary on-delay function in that the input can be discontinuously asserted. This is pretty important and bears repetition. I say again, The cumulative on-delay function differs from an ordinary on-delay function in that the input can be discontinuously asserted. The accumulator maintains a running tally of the elapsed time. Let's now examine the reset feature afforded by this timer. Let's say an operator presses and holds start for 3 seconds and then releases it. In this case, the accumulator has accumulated 3 seconds of a total 5-second countdown. After a pause, let's say an operator opens stop. In this case, the timer is completely depowered and the accumulator is dumped. When power is restored to the timer by closure of the stop button, the cumulative on delay begins anew and the accumulator is reset to 0 seconds. Opening stop therefore serves to reset an ongoing cumulative on delay and clear the accumulator. Besides making some stupid lights blink, a timer executing the cumulative on delay function can also be used to perform some industrial task. Consider a maintenance procedure that must occur periodically, for example changing oil or a filter every 100 hours of runtime. A timer performing the cumulative on delay function can keep track of the elapsed time and notify maintenance personnel the service needs to be performed despite the system being run discontinuously over a period of several days or weeks. Allow me to demonstrate. Rungs 1 and 2 contain a regular 3-wire control circuit that selectively energizes or de-energizes the F contactor coil, as well as the coil of a regular control relay, CR1. When an operator presses and releases start, the F contactor coil will be energized, the F primary contactor will close, and the coil of control relay CR1 will be energized. Rungs 3 and 4 contain a timer executing the cumulative on-delay function set to 100 hours. The mechanically interlocked service reset button serves to completely depower the timer and reset and clear the accumulator. Contact CR1A, associated with regular control relay CR1 in rung 2, energizes the timer auxiliary controlling input. This is the input signal that lets the timer know it needs to pay attention and keep track of the accumulating run time. Rungs 5 and 6 contain the diagnostic notification and reset circuit. The closure of either contact, TR1A associated with timer relay TR1, or CR2A associated with regular control relay CR2, also in rung 5, serves to energize the coil of the regular control relay CR2 and a red light that says Service System. Note that opening the mechanically interlocked service reset button would also de-energize both these devices. Note the de-energized start state of this system at 0 hours as the motor is off, the timer is powered up, and the service system light is off. At the start of a 10-hour work shift, an operator presses start. This energizes the F contactor coil and the coil of regular control relay CR1. Their associated contacts immediately change states. The F primary contacts close and the system springs to life. The F1 holding contact closes and allows an operator to release the start button. Similarly, contact CR1A closes and energizes the controlling input of timer relay TR1. Time in the accumulator begins to collect. Note that contact TR1A remains open since the delay period of 100 hours has not been achieved. The coil of control relay CR2 and the service system light therefore remain de-energized. At the end of a 10-hour work shift, the accumulator has accumulated 10 hours. An operator presses and releases stop. This de-energizes the F contactor coil and the coil of control relay CR1, and their associated contacts immediately return to their deactivated states. The F primary contacts open and the system grinds to a halt. The F1 holding contact opens and removes the holding circuit. Contact CR1A opens and de-energizes the controlling input of timer relay TR1. Given service reset remains closed, the accumulator now has 10 hours in the bank. Over the next several days, this process repeats itself. At the end of the second day, the accumulator has 20 hours in the bank. After 3 days, 30, and so on. Every day the system starts as previously, outwardly unchanged. However, the timer keeps track of how long the discontinuously energized system has run. Here is the system status at the very end of the 10th workday at 99.9 hours of discontinuous operation. Just prior to go home time, 100 hours is accumulated. At this point, the timer executing the cumulative on-delay function tells contact TR1A to close. The now closed TR1A contact energizes the coil regular control relay CR2 and the red service system light. Contact CR2A immediately closes and establishes a holding circuit, thereby maintaining the state of CR2 and the service system light. An operator can now shut down the system by pressing the stop button. As previously, this de-energizes the F contactor coil and the coil of control relay CR1, and their associated contacts immediately return to their deactivated states. The F primary contacts open, and the system grinds to a halt. The F1 holding contact opens and removes the holding circuit. Contact CR1A opens and de-energizes the controlling input of timer relay TR1. Contact TR1A opens. However, the coil of regular control relay CR2 remains energized, as does the service system light, because of the holding circuit established by contact CR2A. Maintenance personnel can be dispatched to the system the very next day. The system is locked out and tagged out, and the oil or filter is changed. As part of their maintenance procedure, they press the mechanically interlocked service reset button. Opening service reset in rung 3 completely depowers the timer and resets and clears the accumulator. Opening service reset in rung 5 de-energizes the coil of regular control relay CR2 and the service system light. Contact CR2A opens and removes the holding circuit. When service reset recloses, we've returned to the start state of our system, with the timer powered up and the accumulator back at 0 hours of service. The system can be returned to production, and after another 100 hours of discontinuous operation, the system will automatically notify maintenance personnel of its needs. In summary, the cumulative on-delay function for this circuit is acting like a record-keeping device and frees operator and maintenance personnel from this tedious responsibility. Applications of the cumulative on-delay function are numerous. However, they all generally behave in this fashion. Only after the controlling input has been energized, continuously or discontinuously, for the adjustable delay period, do the associated contacts change states. Alright, that is that for this lecture. In conclusion, this lecture took a brief look at multifunction timers performing the cumulative on-delay function. We introduced the cumulative on-delay function, reviewed general timer functions, learned how to set up an example timer performing the cumulative on-delay function, and finally employed a timer executing the cumulative on-delay function in a couple different illustrated examples. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.